Sorry that I was late, because I have class in the North Campus. I need to rush back. Okay, let's start the tutorial class today. I hope that everyone can hear me. So, in this tutorial class, I would like to walk you through some of the questions in example stage 2. Okay, and you are supposed to have already at least attempt to solve some of these questions. But I'm not going to go through all of them because I don't have enough time. So let me ask, which question you find it difficult and would like me to walk you through the solution? Which question particularly you want me to explain to you? There are totally 1, 2, 3, 4, 5, 6, 7. 7 questions. Anyone?
7.
7.
Yes.
Okay. How about the other? Any other question? I can entertain some more questions, not only one. Maybe I can start with question number 7. Probably I'll go from the last question and then back to the first. Usually the last few questions would be the difficult questions, right? So we start from question number 7. So we have a measurement following the Poisson distribution. I suppose that you've learned about what it means by Poisson distribution in past, okay? With parameter lambda, and the lambda is unknown, and we believe that lambda is either equal to 10 or 12. Now we have a random sample from the population result into this data. There are 6 numbers here, and therefore the sample size should be 6. So there's the typo here. Okay? S1, S2, S3, S4, S5, actually there should be S6. So we have sample of size 6 and observe the sample. And we are asked to calculate the joint probability of what has been observed using each of the 2 possible values of lambda. So where should we start the joint probability? Now, first of all, you need to know what it means by a Poisson distribution. A Poisson distribution is a discrete type distribution. That means it is count. Right? Poisson distribution is used to model count data. And therefore, the joint probability will be just simply equal to the product of their marginal probabilities. So probability this is the joint probability. What is the chance that the first sample results into 9, the second number results into 13, the third number results into 6, and so on? This is what we are asked to compute. This joint probability, because we have a random sample, so that this joint probability will be equal to the product. Now this is the notation of product. The product of their marginal probabilities. Each of the sample equal to the sample value equal to a particular number. We evaluate this probability and then multiply them all together. We get the joint probability. Now, according to what was stated in the question, the population is Poisson. So this probability will be a Poisson probability. I hope that all of you still remember how to write down a Poisson probability. It is equal to e to the power minus lambda multiplied to lambda raised to power of the sampled value divided by the factorial of the sampled value. Right? I suppose all of you have learned this before. Okay? Just let me know if you have anything don't understand. And we can simplify this into e to power 6 lambda minus 6 lambda, because we raise this e to power minus lambda and multiply it for 6 times. So it becomes e to power minus 6 lambda. And then lambda raised to the sum of the powers. Multiply them together, it is just like we raise this lambda to a power equal to the sum of the powers. And divided by the product of the factorials. Now in this question, we are asked to compute this probability with different value of lambda. So this to indicate that this is a probability dependent on lambda, so probably we may write in this form. And from the sample, we already have the sample. We have S1, S2, S3, S4, S5, and S6. So that we can further express this as according to the summary statistics. Using ordinary calculator, we can get the sum of the sample equal to 59. So we can substitute this part. And then we have the product of the factorial And this is a very large number. Okay? I'm not going to write down this result. So we substitute into this, then what remains will be just to put lambda equal to 10, lambda to equal to 12, and then to evaluate this way. So for lambda equal to 10, we substitute lambda equal to 10 into that expression. To indicate that this is a number depending on lambda equal to 10, it will be equal to e to the power minus 6 times 10. 10 raised to power 59 because the sum of the sample is equal to 59. And then divided by this product of the factorial. Then again, using your ordinary or scientific calculator, we can get the result equal to 5.907 multiplied to 10 raised to the power minus 7, which is a very small number. Okay. Usually this joint probability, as long as the sample size is large, if you have larger sample, then this joint probability will be even smaller because we are multiplying a lot of probability together. Okay? Then the next, we substitute lambda equal to 12. We do the same calculation. But this time, this will become e to the power minus 6 times 12. And 12 raised to the power 59, divided by this product of the factorial. And this will become 1.704 times 10 to the power minus 7. So this is how we get this joint probability. You can try to put different value of lambda to it. You will get different numbers. Now, in the second part of this question, we are asked to compare these two numbers. Which one is larger? When lambda is equal to 10, right? So, the probability, the joint probability is larger when lambda is equal to 10. So, if I tell you that lambda can take only two values, either it is equal to 10 or equal to 12, and I ask you to guess which one will be the true lambda, which one will be a more reasonable guess. If the level of lambda will result into the probability very, very small, then of course that is not very reasonable. Like if I tell you that the lambda is equal to 100, but the probability is very small. So if lambda is equal to 100 and the probability of observing this sample is very small, very unlikely to observe this sample, then of course that lambda is not reasonable. So comparing these two probabilities, it tells us that it provides some measure. We call it the likelihood. Later you'll learn it. It tells us that if we are asked to compare these two possible values, 10 and 12, as the guess on the value of the lambda, we will rather choose 10. The reason is that this probability is larger. This probability tells us which one will be a more reasonable guess on the value of the unknown parameter. But if I don't tell you that the value of lambda is either 10 or 12, the value of lambda can be any positive number, then which one will you choose as an estimate of lambda? We'll try to put different value of lambda to it to see which one is the largest. Right? So how can we do this kind of calculation? We use R. In R, there is a very simple command for us to compute a Poisson probability, which is DPOIS, distribution for Poisson. POIS stands for the short form of Poisson. D stands for distribution. And what we need to do is to input the value of x. Like, for example, the first number of x is equal to 9. And of course, you also need to input the value of lambda. Value of lambda equal to 10, for example. This command will tell us the probability for a Poisson distribution with lambda equal to 10, the probability of getting a 9 from this distribution. This is how you get a Poisson probability. And if you want to compute this Poisson probability for a set of lambda to observe the sample, then you can input a vector to it. 9, 13, 6, 8, 10, 13. All this will be put in the solution. That will be uploaded. That was already uploaded to Blackboard, I guess. So this will return a set of the Poisson probability with lambda equal to 10, evaluated at 9, 13 with the x value, evaluated at 9, 13, 6, 8, 10, and 13. So these are the probabilities. Probability x equal to 9, this one. Probability x equal to 13. Probability x equal to 6, 8, 10, 13. Now we want to compute the joint probability. So we multiply them all together. Use the product function. So a single command will get what we computed before. And you can change the value of lambda. For example, to 12, we get the previous computed. So you can use R to verify your hand calculation. Okay? Now actually you can try, because the computer will do it all the work for us. You can try 13. You can try 9. You can try 11. You can compare this probability. You see that this one will be still the largest. The one with lambda with 10. So among all these lambda, 10 seems to be the most reasonable choice for the value of lambda. If we are given this sample and asked to guess the value of lambda. Of course, there will be some other value. If you put 9.833 into it, you see that we can get a probability turned out as this. And later on, in the course, when you learn about what we call the maximum likelihood estimation, then you will know how to get this number that maximizes the probability. Okay. Any question about question number 7?
Sorry.
Yes?
Can we just compute the sample mean and sample variance without computing joint probability?
You don't need the mean and variance to compute the joint probability.
Yeah. I mean, in this question, can we just calculate sample mean and sample variance? So, and we just compare it to population mean and population variance.
To compute the sample mean and sample variance and compare to the population mean and population variance, and then?
And we can get which one is is more accurate?
More accurate. Yes. That's the case if you know the value of the population mean. Okay. In practical situation, you don't know the population mean, right?
Yeah, but in this question, it tell us is 10 or 12.
Yeah. In this question, of course, we know that it is the population mean. No. Actually, in this question, the population mean is unknown because we don't know the value of lambda. We are only told that lambda can be either 10 or 12, but we still don't know whether it is 10 or 12. Right?
Yeah.
So that means you don't know the mean is 10 or 12. You don't know the population mean.
But I think it is 12.
Yeah, it will be either 10 or 12.
Yeah.
But we don't know which one is the correct one.
Yeah.
Yeah. And then we are comparing which one will be more reasonable.
Yeah.
By computing this topic.
I mean, maybe we can just compute sample mean and sample variance, and if it's closer to 10, it means 10 must be the population.
Well, you can do that for comparison. Yeah. If you are only given two numbers. As the possible value of lambda. But in practical situation, actually we are not given just two lambda. We may have no idea on the value of lambda. It may be just the whole side of the positive real line, right? Then in that case, we may not be able to use this kind of metric to compare just based on the sample mean and sample variance to determine the most reasonable guess. But later on you'll see, actually the sample mean will be the best choice as an estimate of the population mean, according to this kind of calculation. Okay?
Thank you.
Any other question? So now, let's just maybe any other question you want me to walk through besides question number 7? Maybe I just move forward from 7 and then to 6. Oh, I change it back to this screen. Now question number 6, the description is very simple. We have a sample of size 10 from the uniform distribution from 0 to 1. And we want to calculate the mean and variance of the sampling distribution of the sample mean. After you had already learned from the lecture what is the meaning of the sampling distribution. Now, sample mean itself is also a random variable, so it will have an own distribution, and we call this the sampling distribution. And it may not be the same as the population distribution. So we have a sample from the uniform distribution, but the sampling distribution of the sample mean may not be uniform. But we have general property of the sampling distribution of the sample mean. We know that the expectation of the sample mean is equal to what? What is the expectation of the sample mean for a random sample? A general result, general property from the theory that was described in the lecture.
Population.
Yeah, the population mean. And what is the variance of the sample mean? It is also related to the population variance.
Population variance divide.
Yeah. For any random sample, the expectation of the sample mean must be equal to the population mean. The variance of the sample mean must be equal to the population variance divided by the sample size. It is a mathematical fact. So in this question, we have a sample of size 10, then of course the sample size is equal to 10. But in order to get these two numbers, we need the population mean and also the population variance. And the population is uniform, so we just start from the very beginning. To find the mean, the population mean is just equal to the expectation of any random variable drawn from this distribution. this is the general formula for computing the expectation or the population mean based on a probability density function. Because uniform distribution is continuous, so we use the probability density function. For discrete type random variable, for discrete type distribution, then this one will be the probability mass function, and the integral will become a summation. But for continuous distribution, we use this. Now, what is the density function of uniform, CO1? Anyone have any idea? The density function, the probability density function of uniform distribution from 0 to 1. Uniform, right? Uniform means all the same. If you draw it in a graph, it is a horizontal line, a constant.
1 divided B minus A.
Yeah, 1 minus B minus A. And it is 0 to 1 because B is 0 to 1 and A is 0 to 0. But this will be equal to this value just when x is within the range. If x is outside the range, the density function is equal to 0. This is the density function of the uniform distribution. So we substitute into this integral. Now, in general, the integral is over all the real numbers. But outside this range, the probability density function fs is 0. So that means the range of the integral will be just from 0 to 1 only. Because outside, all the things will become 0. So this is how we obtain the expectation or the population mean for the uniform CO1 distribution. And the rest will be just elementary calculus equal to half. So the population mean for uniform CO1 is equal to half. Okay? Now next, we also need to find the variance. To find the variance, we start from the very beginning. We can start with the expectation of the square of x, which is the second moment. This is an intermediate step for us to determine the variance of a random variable or a distribution. Expectation of the square of that random variable. And it is equal to, in general, equal to this. Whenever you want to find an expectation, you just copy the function in terms of x, multiply it to the PDF, probability density function, integrate over all the possible values. Now in this question, the density function is equal to 1, within 0 to 1, for a uniform distribution. So the rest will be elementary calculus equal to 1/3. Now this is not the final result for the variance. It is just an intermediate step. Just keep in mind that finding the second moment, the expectation of the square of x is just an intermediate step. From my past experience, I find that a lot of students always terminate the calculation here. This is not the end. You also need to determine the variance. And this is the formula for calculating the variance. I guess all of you should have already learned about this before, right? The variance is equal to the expectation of the square of S minus the square of the expectation of S. This is a commonly used formula for calculating the variance. And we already have all the ingredients computed. So that the variance is equal to 1 over 12. So finally, we have the expectation of the sample mean equal to half, the variance of the sample mean equal to sigma square over n, sigma square over 10, because we have a sample of size 10, which is the reciprocal of 120. So for any of this kind of problem, as long as you understand how to get the mean and variance, and how to get the expectation of the sample mean, variance of sample mean from the population mean and population variance, and the calculation will be exactly the same. The only difference is the content of the interval, according to different probability density function. Any question? Okay. Then we move backward to question number 5. Now, question number 5 actually is a very, clumsy question. Now, first of all, we have a population. Now, this time we are given a population of size 5, 3, 7, 9, 11, and 15, kind of symmetric. And in part A and first part, we are asked to calculate the population mean. So what is the population mean? When you have a population, you have some discrete values in the population. The population mean is just simply the arithmetic mean of all these numbers in the population. So that the population mean is simply equal to 9. And actually 9 is also the median. So that's why in the description of the question, the distribution here is symmetric, so that the population mean and median are identical. Okay? It is the population mean. And the median is also equal to 9. It is symmetric. Now part 2 is quite clumsy because we are asked to write down all the possible samples of size 3 drawn without replacement from the population. You know what I mean by drawing a sample without replacement. We don't have to repeat it observation in the sample. So, for example, if you have drawn the 3 included in your sample, then you won't have another 3 because there's no other 3. You cannot have a double 3 in your sample. That's the meaning of drawing without replacement. You draw the 3, and then you don't put it back when you draw the next one. So the next one will be drawn from 7, 9, 11, and 15. That's the meaning of drawing without replacement. In contrast to drawing with replacement. If you are drawing with replacement, every time you are drawing from the 5 numbers. So it is possible for you to get all the 5 numbers into the 3. But drawing without replacement in this example, because all these numbers are distinct, so you don't have repeat numbers in your sample. So we list out all the possible samples. So the first 3 numbers, and then we change 9 to the next number, 11, 15. And then we change 7 into the next number, 9. And similarly, sorry. Yeah. Yeah, I had missed one of them. 3, 7, 9, 3, 7, 11, 3, 7, 15, 3, 9, 11, 3, 9, 15, and then 3, 11, 15. Yeah. And then 7, 9, 11, 7, 9, 15. I missed the 7, 9, 15. So totally there are 10 possible samples. If we draw 3 numbers without replacement from the population of size 5, it is just a combinatorial number. If you know a little bit about counting, 5C3, that will be equal to 10. So totally there are 10 possible samples. Next, we are asked to calculate the mean and variance of the sampling distribution of the sample mean. So we can write down the value of the sample mean for each sample. The sample mean of 379, it is equal to 3 add to 7 add to 9 and then divide by 3. And this will be 21 divided by 3, 23, 25. So these are just routine calculations. Sorry. This is not 31. This is 27. Yeah. And then we have 31, 33, and then 35. So this will be the sample mean that we will obtain for each of these possible samples that we collect. So in other words, if you draw a sample of 3 without replacement from this population, if you get this one, then the sample mean you obtain will be equal to this. Now, in order to find so these are the possible values of the sample mean we will get. But we all need to know their probability so that we can compute their expectation and also the variance. So what is the probability of obtaining each of these samples? We have 10 possible samples. We are drawing without replacement, without any preference. We just randomly draw the numbers. So all these 10 samples should have the same chance to be collected. So each of them will be obtained by a probability of 1 over 10. Now we have the probability of 1 over 10 to get a sample mean 13 and 19 over 3. We have another 1/10 probability to get a sample mean 21 over 3 and so on. Then you can just make use of this to compute the sampling distribution, the sample mean, the expectation of the sample mean. we multiply each possible value to its probability, to the corresponding probability, and do this for all. Each of these sample mean multiplied to the corresponding probability, and then we add them up all together. So this is 23. And you can try to work out the tedious calculation. You get this number. So this is the, sorry, I copied the wrong number. It should be equal to the population mean, so that it will be equal to 9. You can try to do the calculation. Add up all these numbers and then divide by 3 and divide by 10. You will get 9. Exactly equal to the population mean. And this is the general property. Okay? As I mentioned before, if you have a random sample, then the expectation of the sample mean will be equal to the population mean. Now, besides this, we are also asked to compute the variance. Rather than we get the variance, we do the same thing as before, but this time we are talking about a discrete case. So the expectation of the square will be equal to the square of each of the expectation of the square of the sample mean will be equal to the square of each possible value of the sample mean, multiplied to the corresponding probability. So these are not difficult, but quite clumsy, right? Now, as I mentioned before, this is not the end because this is just the second moment. This is just the expectation of the square of the sample mean. In order to find the variance of the sample mean, we need to determine this. The expectation of the square of the sample mean minus the square of the expectation of the sample mean, we will get the variance. The variance is equal to 2.667. Actually, it is a more exact number is equal to 8/3. If we don't use this form, decimal form. Any question? Actually, we also seen a formula. If we draw without replacement, with sample without replacement, then the sample mean will have an expectation equal to the population mean. But unlike the previous situation, we have seen a formula that variance of the sample mean due to sigma square over the sample size. But that is for the case of sampling with replacement or sampling from an infinite population. But if we are drawing without replacement from a finite population, then we will have a finite population correction factor. Okay. This is the general result of the variance of the sample mean if we are drawing without replacement from a population of size capital N. I guess you've seen this before. And you can try to put the result of the population of the population size equal to 5, sample size equal to 3, sample size equal to 3, and the population variance equal to 16 into this, you'll get exactly the result H over 3. Is there any question? Now, in the question, besides calculating the sample mean, the expectation and variance of the sample mean, in part 3 we are asked to also calculate the mean and variance of the sample median. So we can do the same calculation as before. But this time, instead of using the sample mean, we use the sample median. So we denote the sample median of Q.5 because the sample median is the 0.5 quantile. So the median will be just the number at the middle, at the center, at the central wang with a central wang. So the median of this sample is 7. Median of this sample is also 7. 7, 9, 9, 11, 9, 9, 11, and 11. So these are the sample medians. So instead of using this column, this time you can use this column, and you can try to find out the expectation of this median and the variance of this median, doing the exact same calculation as before I showed you, and then you can compare with the result for the sample mean to see which one will give you the number closer to the mean, which one will give you a smaller variance. And I'm not going to go through because I don't have time remaining. Is there any question? So what I've shown you in this tutorial session as a solution of this example sheet, all this the typed solution have been already uploaded to Blackboard. So whenever you encounter any problem or you have any question regarding to the course material, just feel free to contact me through my email. So see you next week.
But the finally said this.
Yeah.
What is the situations we use it?
We draw without replacement.
Without
replacement, then
like
this will be the formula.
This is population.
The population size, yeah, sample size.
And what is this?
This is for sampling with replacement.
Yes.
Or if when the population is so large and with infinite size, then sampling without with replacement are different. Then you can use this one. In fact, if capital N is